All right, we're going to start the Chapter 9 Homework B review. This is the last one of the semester, lucky number 13, as we get ready for the final exam this week. So this assignment dealt primarily with structures and properties of solid state materials, focusing mostly on crystalline materials, and a few other topics related to the different classifications and bonding in those types of structures. So the problems I'll go over are mainly dealing with the crystal structures, the cubic unit cells or other types of unit cells that we covered. That seemed to be the topic that give us the most difficulty on this. But there's, again, a few other topics covered that you want to make sure you're clear on as well. The average this week was pretty good, close to 10 out of 12, and so I identified a few problems here where we had success rates of 50% or less on the assignment. All right, so let's get into it then. So the first couple problems deal with one of the ideas we talked about in class about how these different three-dimensional crystal lattices are formed, which is by taking layers of atoms, two-dimensional layers, and stacking them in different ways. So the two problems deal with the most important type of layer stacking that we need to know about, which is what are called the close pack arrangements. So in this approach here, what we do is we take what's called a close pack array of atoms. So I'm going to try to draw one out. As you guys know, I'm not a very good artist, but basically we have a layer of atoms, and what we do in these is we stack them as close together as we can. So basically each row is sort of offset from the previous, so that you have atoms sort of sitting in the divots of the above row. And so then what ends up happening in this is, in the way that you can sort of quickly recognize that this is a close pack layer. So this is one close pack layer. So imagine if you had a bunch of marbles and you were trying to lay them out on a flat surface as close together as possible. This is what it would look like, and what you can quickly recognize is that if you look at one atom in that layer, which I'll show with the red X here, it's going to be surrounded by 6 others. So when we look at this picture here that we're asked a question about, so we're looking for which of these correctly describes the lattice arrangement shown below using this sort of layered type of approach, we can notice again that one atom in each layer is surrounded by 6 others. So we know that this is a close packed layer. Then we just have to identify what type it is. So when we have these close packed layers, there's sort of 2 major ways we can stack them together. So one is called ABA stacking. So in ABA stacking, what we do is we stack one layer, we stack the next layer offset from it, and then we repeat the pattern. So basically the pattern repeats itself every 2 layers. So you have 2 layers that are offset, and then it repeats. So when we do ABA stacking, that's called hexagonal close packing. So that gives a unit cell that is not cubic but hexagonal. Then the other type is ABCA. So that's where we're going to stack 3 layers offset from each other, and then we'll start repeating the pattern. So basically you have 3 offset layers and then a repeating pattern. So each repeating unit is 3 layers in this case, and that's what we would do to get cubic close packing. So the packing densities are the same in both. They both occupy 74% of the total volume, but they give slightly different unit cells. So in this picture here, we're using different colors, and we didn't specify it, but all these colors represent the same atom, just showing you how the different layers are. And so in this structure here, we can see that there's layer A is labeled as yellow, then we'll have B in blue, C in green, and then back into A. So this is ABCA packing. That's the type that we're talking about here. So that's going to be cubic closest packing. So it's not ABA. We have 3 alternating layers before we repeat. Body-centered cubic is not a close packed structure, so we couldn't make body-centered cubic from these types of close packed layers. So ABAC, that's not one of the options. And then finally, the only option that works is choice C, cubic closest packing. So when we have this ABCA stacking, we get cubic closest packing. Now the next question is really about the same thing, but this time we have a slightly different picture. This time we can see that we just have 2 alternating layers. So we'll call yellow layer A again, and then we have layer B, which is offset, and then as the colors are kind of hinting at, we're going to repeat that pattern. So it's ABA packing this time. All right, where it's just 2 alternating layers and then a repeating of that. So in this case, again, ABA means that it's hexagonal. And so it's not a cubic unit cell. It's not ABCA in this case. That was what we had in the last problem. And it's not simple cubic. Simple cubic unit cells are not made from close packed layers again. In simple cubic cells, the layers look like this, where they're completely eclipsed on each other, so they have little gaps in between. And so you make these squares that you then stack on top of each other, but they're not the same as these layers up here where the atoms are as close together as possible. So it's not simple cubic, it is cubic, in this case it's hexagonal, so it's not cubic at all. So that's wrong. And then so the only one that works is B, hexagonal closest packing. So when you do this ABA stacking, that's what you get, is hexagonal close packing. So these first two problems dealt with, again, the idea of using two-dimensional layers and how those are built up to make these structures. Most of the problems then deal with actually understanding how the unit cells look like, in particular the cubic unit cells, which is what the vast majority of these problems were about. So these next few deal with counting atoms that are located in a cubic unit cell. And so the first one here is probably the most straightforward one. If you have an atom located at the body center of a unit cell, it's shared equally between how many unit cells? The options are 1, 3, 4, 2, and 8, where option A is it also means it occupies only the main unit cell, not its neighbors. So in a body-centered position, you have your cubic unit cell. Again, my ability to draw cubes is lacking, but we'll do our best. It's not quite a cube. Alright, anyway, close enough. Alright, so that's close enough to a cube, apologies for that. But if you have a body-centered position, it's directly in the middle of the cube. Again, hard to see it in 3 dimensions when I'm trying to draw it on a flat screen, but nonetheless it's right in the middle of the cube, completely enclosed by the unit cell. So for body-centered position, that's going to be not shared at all. So it's only going to occupy one cell. It's not going to be bordering between 2 or more cells. So choice A is the correct one here when you have a body-centered position. Now for the next one here, I put a little graphic in to help us. This graphic was not given in the problem, but I put it in here to help understand it. So now we want to know how many unit cells share an atom which is located at the center of a cube edge. Alright, so you're talking about a cube edge. So this is what this picture is showing is 8 cubic unit cells stacked together. So 4 on the top, 4 on the bottom. And what we're talking about now is an edge position. So edge is going to be, for example, right here, right along one of the edges of the cube. And we want to know, again, how many unit cells share that edge position. And so what we'll see is that this edge is located on the shaded blue sphere. It's bounded by the one directly behind us. This is 1. Let me draw these in red again so it makes it easier to see. Alright, so if we call this unit cell number 1, which is the shaded one, right behind it is 2, to the right of number 1 is 3, and then behind number 3 we'll call number 4. So there's 4 cubes that share this one edge here that I put the red dot in. So when you have an atom that's located on the edge of a unit cell, it's going to be shared by 4, and that's why we count it as 1/4 when we're counting. Alright, so that's going to be the edge position. The other major one, which didn't come up here, would be a face position. So if we look at the center of a face, like right there, again, I'm trying to do it in different colors, I keep messing up. So this center of a face right here, it would be shared by 2 cells. This one on the bottom left, and the one right next to it on the bottom right, but not any of the ones behind it. So faces are shared by 2, but edges are shared by 4, as again I showed up here with the first red dot. Alright, so for cube edge is going to be shared by 4. So counting the different positions in a cell and knowing how they're shared between neighboring unit cells is one of the more important things we want you to understand from this part of the course. So then the next few problems deal with actually counting how many total atoms are in different types of cubic unit cells. So the first one here wants to know which equation represents the number of atoms in a primitive cubic cell. I hope you can see the answer choices okay. I just screenshotted them so it's a little bit easier to format it that way, in the way that it is in Blackboard. But again, here we're talking about primitive cubic. We want to know how do we count the atoms in a primitive cubic cell. So in a primitive cubic cell, what we have to remember is that all we have are just the corners occupied. Alright, so the primitive cubic cell, there's your cube, and what you have in a primitive cubic is just one atom on every corner. Alright, and so in that case, the only thing you have to count are the 8 corner atoms. So the number of atoms are going to be, each corner atom is shared by 8 unicells. So again, that's helpful to look back at this picture here. So if we look at, let me do it in a different color now. If we look at, for example, this one right in the middle here, this is on one of the corners, and I'm going to highlight it in green so you can hopefully see it a little bit better. That position there is shared by all 8 of the cubic unit cells that are shown in this diagram, the 4 on the top and the 4 below it. So every corner position, when you extend it out in all directions, is shared by 8 unit cells. So when we count atoms in the corners of unit cells, there's going to be 8 corners, and each count is 1/8. So it would be 1/8 times 8. That's the portion that it belongs to that unit cell because it's shared by 8, and that's the number of corners we have. There's 8 corners in a cube. So it's 1/8 times 8, or 8 times 1/8 is how I usually wrote it. But either way, that would be answer choice A here. The rest of these deal with other fractions and other parts of the unit cell that are not relevant to simple or primitive cubic. Next question, very similar. This time we're talking about body-centered cubic cell. So in a body-centered unit cell, did a better job drawing it there, didn't I? Alright, I'm proud of myself. Okay, so then what we have in a body-centered cubic cell is, in all of the cubic unit cells, we have all 8 corners occupied. So when you're counting atoms in these, you're always going to have 1/8 times 8 as part of the counting. But then in the body center, again, a little bit harder to draw in 2 dimensions, but you have one right in the middle as well. Same thing, but I'll draw it with a solid sphere just so you can distinguish it. But that one is directly in the middle, and as we talked about earlier, atoms that are in the middle are not shared at all. So when you're counting the number of atoms in a body-centered cubic cell, you have one in the middle that counts as a whole atom because it's completely enclosed by that unit cell, and you have the corners that count as 1/8 each. So you have 1/8 for each of these corners, 8 total corners. So all of them should have 1/8 times 8 in it, which most of these answer choices do, but in body-centered cubic you have the additional 1 in the center, so that's why we would pick choice C for this one. Alright, so that's counting the number of atoms in a body-centered cubic cell. And then finally, this is just another way to ask the same question. So we could also just ask it numerically instead of asking for the formula or the way that we count it. So if you have a body-centered cubic cell, how many atoms per unit cell is that? Well, as we just said, now it's just a matter of doing the simple math. 1 in the center, all 8 corners, so 1 plus 1/8 times 8 is a total of 2. So in body-centered cubic, there's 2 atoms per unit cell. So I did give you, a table in the notes that has all this information in it, how many atoms per unit cell, how are they counted, all that stuff. If you want to just memorize it, be my guest. I think it's helpful to understand the structures and be able to visualize them. And so hopefully what I've gone through here helps with that a little bit. But you just need to know some of these parameters. And again, counting the atoms in the cell is one of the more important things we expect you to be able to do. Now the next couple of questions deal with geometric aspects of these cubic unit cells. So how does the length of a side in a cube? So remember, in a cube you have all the side lengths are identical. That's what makes it a cube and not any other type of geometric shape. Alright, so if you have in a cube, each side is the same length, and we abbreviate that as A, typically speaking. So then the volume of the cube would be A cubed, and so on. So you need to know, if you want to know the volume of the unit cell, you need to know the side length, and the side length is going to be related in some way to the atomic radii that make it up. So here we're looking for the distance in terms of r to the atomic radius along an edge of a primitive cubic unit cell. So again, in a primitive cubic cell, we've already diagrammed earlier, you just have one atom in each corner. Now when I draw them out like this, I draw spaces between the atoms just to make it easier to see and easier to draw, but in reality, the atoms are completely adjacent to each other. They're going to be touching each other with respect to wherever their, outer electrons reside, whatever their radius is. And so if we look at one face of a cubic unit cell, a primitive cubic cell, I should say, what you have in this case is, again, one atom in each corner. So each corner is going to have an atom at the center of it, and they're going to be sort of touching along the corners like this. So I did not do a particularly good job, as usual, of drawing because I failed kindergarten for my poor motor skills and things like that. But anyway, that's what it's going to look like. So each of these little boundaries is a part of a sphere. Again, you have the rest of it sort of outside or shared with the other unit cells. But if you look at one face of the cell, that's what it's going to look like. And so, again, this is our side length A here. And as we go across the length of the side, we have one atomic radius to get to the center, a second atomic radius to get to the other corner. And so in a primitive cubic unit cell, A is equal to 2 times the radius. And that's because, again, we have 2 atoms, one in each corner, that sort of touch in the center of that side. And so A is equal to 2R here. And so that would be choice B here, 2 times R for the distance along a primitive cubic cell. So this is kind of a little bit more advanced of a topic than just counting the atoms in the cell. This takes you a little bit further. We went through this in class, but it is a little bit more advanced. But nonetheless, for a primitive cubic cell, that relationship is very simple. And the next one is similar here, and it wants to know the distance across a diagonal face of a face-centered cubic unit cell. So face-centered cubic unit cell, we kind of referred to it earlier. It's the one that involves ABCA packing of those close packed layers. But what it looks like in terms of a single unit cell, which is what we're more interested in, is going to be like this. So we have cubic unit cell, and in face-centered cubic, you have, again, one atom in each corner. That's always going to be true. But then in addition, I'm going to draw these in green just so you can see them better, although, again, in reality, they're the same atom, just in different locations. We'll have one on the center of each face, which, again, is a little bit hard to draw in 2 dimensions individually. But there's 6 faces on a cube, and each of those faces, this one on the right here is probably the easiest to see, each of those faces is going to have one right in the middle. So then if we look at the face, this is asking about the diagonal across a face. When we draw one face of a face-centered cubic unit cell, this time what happens is you have, and I'll do it in red again so you can see the atoms better, you have atoms along each corner, but there's actually a little bit of a gap in between each one now. And the reason there's a little bit of a gap is because you also put one right in the middle. Alright? So imagine all those are the same size. I didn't do a great job of drawing it, but you get the idea. But this is what the center of a face-centered cubic cell looks like. So the side length A is no longer a simple function of the radii because you have a little bit of a gap here, as I said, to be able to fit this other one in there. But if we go across the diagonal, which is what we're looking at now, there is a geometric relationship. The face diagonal is a square root of 2, but this is asking for it in terms of atomic radius. So as we go across the diagonal, we go through one atomic radius, we go through 2 more to get through the center atom, and then we go through another one to get to the corner. So in total, it's 4 radii to get from corner to corner across the face diagonal. So the relationship here is that A is equal to 4 times the atomic radius, which is choice B. Alright, so that information is in the notes. It wasn't in the little summary table that I gave you. But if you can visualize these structures, then it's a little bit easier to be able to come up with answers to some of these problems here that deal with the geometric relationships between the length of a side on the cube, which is A, and the atomic radius, which here is the radius, lowercase r. Alright, the last 2 problems deal with ionic structures. So we've talked about cubic unit cells, and everything so far has been relevant to just a pure element. So a metal typically that occupies these types of structures where you have, again, different possibilities, simple cubic, body-centered cubic, face-centered cubic, and so on. And the other type of structure we talked about at the very end were the ionic structures, where you have 2 different ions in the unit cell occupying different positions. And so the way it typically works is one of the ions most often the anion, but it can be the cation as well. It'll be defined for you in the problem. One of the ions occupies one of those typical unit cells, and for ionic structures, it's either going to be primitive cubic or face-centered cubic. Those are the only two options. And then the second ion, one of the opposite charge, is going to occupy one or more of the holes in that structure. And so in problems like this, what we'll typically do is we'll describe the structure to you, and we'll ask you to then figure out how the ions are counted. So this one here is a request from a student, but it's a good one to cover because it is relevant to the last one I'm going to do, and it's an important type of question to have. And so here we're talking about calcium sulfide has a face-centered cubic unit cell with calcium ions in octahedral holes and sulfide ions at the lattice points. How many ions of each element are contained in each unit cell? So for problems like these, it's still helpful to remember things that we learned a long time ago. This feels like a totally new and totally foreign topic, but it is still related to ionic compounds. And we learned about ionic compounds back in chapter 3. We didn't know anything about their structure, anything about cubic unit cells and stuff like that, but we knew how to predict the formula of an ionic compound and how to balance the charge and all that stuff. So I think in problems like this, the first thing you should do is figure out what is the formula for the ionic compound that I'm considering, because however those ions are arranged in a cubic unit cell, you need to have the right ratio of cations and anions to balance the charge still. So let's look at calcium sulfide. So calcium sulfide, we have to remember the symbol for that. That's going to be calcium and sulfur. If we go to the periodic table, which I did not open up, where is it here? Where's my periodic table? Come on, somewhere. There it is. Sorry, my icons are too small. My eyes are too old. Alright, so here we go. We need to find the charges of the cations and anions. So we would have learned, again, a long time ago, how to predict the formula for calcium sulfide. Calcium is in group 2, so it will form a +2 cation. Sulfur is in group 6, so it will form a -2 anion, gaining 2 electrons, gets a noble gas. This one losing 2 electrons. Alright, so this formula here is going to have a +2 and a -2 cation and anion, which means then if we, again, cross the charges and make them into subscripts, we get calcium 2S2, but the ionic formula I always written as empirical formula, so CAS is the formula for this ionic compound. And that's helpful to keep in mind because whatever answer we pick, I think this was multiple choice, but I didn't reproduce all the answer choices. I'll just go through it in sort of free response form. But whatever answer we pick needs to have equal numbers of calcium and sulfur. So again, there might not be exactly one of each in the unit cell, but there's going to be the equal number of both. All right, so here what we have is calcium sulfide has a face-centered cubic cell with calcium ions in octahedral holes and sulfide ions at the lattice point. So when we say that sulfide ions are at the lattice points, that means the sulfide ions occupy the face-centered cubic cell. So in this structure here, if we draw the cube, I'll try to draw it a little bit bigger this time, so it gives us some more room. So again, it's helpful to visualize. You don't really have to as long as you remember the rules for counting and how the different holes work and all that stuff. But what this structure would look like is going to be something like this, a cube, and then face-centered cubic. So I'm going to do sulfide in red here. It's going to be on the face-centered cubic position. The structure is going to get a little bit crowded. So there's the 8 corners and the 6 faces. 1, 2, 3, 4. And then, which one did I not do yet? God, front center and back center. So again, kind of a crowded cell, but it's face-center cubic. It's hard to draw it in 2 dimensions. And then we say that the calcium ions are at the octahedral holes. So the octahedral holes are located, we have to know the locations of these different holes in the cell. They're located on each edge. So I'm going to do calcium in green here. So each edge, 12 edges in a cube. Let's see if I got all of them. 1, 2, 3, 4. 1, 2, 3. There should be one more in the back edge there. All 12 edges and then one right in the center. Okay, so again, super crowded, super hard to read when I try to sketch it out in 2 dimensions like this. But the important part here is to count them. Alright, so for sulfur here, which is S2 minus, is face-centered cubic. So what you're going to have is, again, all 8 corners are occupied, counting as an eighth each. And then we have, in the face center cubic, all the faces are occupied. Faces count as a half each because they're shared by 2 unit cells. Again, back to this picture up here that I did earlier. The faces, which I'm showing in this bottom red dot here, are shared by 2 neighboring cells on either side of the face. And so those are going to count as a half each, and there's 6 faces. So in total, we have 4 S2- anions in the unit cell. Now, because the formula is calcium sulfide, 1-to-1 ratio, we should also have 4 calcium 2+. So let's see if that's true. Again, the picture up above is probably pretty useless at this point because of how crowded it is. You should look at the real picture that's drawn better than I can do it by hand. But for calcium 2+, if we know that it's in the octahedral holes, which this problem is telling us, then what we can do is, again, count those positions. So the octahedral holes, as we said, are along all 12 edges. Edges count as a quarter, as we talked about earlier. But then there's also one octahedral hole right in the middle that I drew, so that counts as 1 total. So that also adds up to 4 calcium 2+. So in this problem here, the correct answer, however it was sort of formatted in the answer choices, would be 4 of each. 4 cations, 4 anions. They have to be equal because that's what we need to balance the charge. And the number 4 comes again from which positions in the cubic cell they occupy. Face center cubic is 4. Filling up all the octahedral holes is also 4. Okay, so that was a good problem to go through to help understand how we count ions in an ionic structure. And then this one here is going to be a very similar problem. So we have a partial diagram. This time I have to read the picture. For zinc sulfide below, determine the empirical formula and how many empirical formula units are present in one cell respectively. And it says, note, zinc ions are inside of the cell. So again, that's going to be important when we count them. Alright, so in this search here, again, we can think about the formula of the compound, zinc and sulfur. As we said in the last problem, sulfur is S2-. Now, zinc is not the most obvious one based on its location on the periodic table. It is a transition element, and we said most transition elements can have multiple charges. But for zinc, it's sort of the rare exception where it's a transition metal that only has one possible ionic charge, which is +2. So zinc has a 4s2 3d10 valence configuration, and the most stable cation for zinc is formed by just losing those 2 4s electrons, making a 2+ cation. So this is one that we did expect you to know, though it's not the most obvious one, but zinc is always going to be 2+. And so again, this is going to be a structure here where the empirical formula is a 1-to-1 ratio, zinc sulfide, just like calcium sulfide above. So we can eliminate a few answer choices because they have the wrong empirical formula altogether. So if you can predict the formula of the ionic compound, which again you should be able to do based on what we learned in Chapter 3, then in many cases you can eliminate answer choices just based on it having the wrong formula. So A, B, and E here all have the wrong formula, so they can't be correct. But then C and D have the correct empirical formula, and we have to decide, is there one formula in the U cell or is there more than 2? So again, that's going to come down to counting the atoms. So in this structure, again, the sulfur 2- anions are once again on the face center cubic positions. All 8 corners, and then all 6 faces. Okay? So it's going to be counted the same way. You have all 8 corners counting as an eighth each, and you have all 6 faces counting as a half each for a total of 4. And then for the zinc 2+, these are located in what are called tetrahedral holes. So we're telling you as a hint that they're inside of the unit cell. That's the most important thing for counting. They're basically located near each corner, and they're called tetrahedral because they have 4 nearest neighbor sulfur atoms. 1 from the nearest corner, 3 from the nearest faces. So 1, 2, 3, 4 if we're focusing on that one there. Okay? So those are called tetrahedral holes. You should know that as well. But the important thing is counting them, and for tetrahedral holes, all of them are inside of the unit cell, as the hint tells us. And we see in this structure that there's 4 of those purple dots, which are going to be the zinc ions. Okay? And that's color coding that tells us that it's zinc. So zinc is in the tetrahedral holes. Only half of them are occupied, but that's going to be a total of 4 as well. So in this case, the formula is zinc sulfide. There's going to be 4 formulas per unit cell because there's 4 of each ion in the cell. And so the correct answer would be choice C, empirical formula is zinc sulfide, in this case more than 2, or more precisely 4 per unit cell. Alright, the last problem we're going to go through is the only one that we had difficulty with that wasn't about cubic or hexagonal crystal structures. It's about bonding in metals. So it wants to know which statement or statements concerning metals is incorrect. So the key idea about the bonding in metals is that you have delocalized electrons. So the valence electrons in metals are loosely held. You have these different regular arrangements, usually cubic or hexagonal, of the atoms, and the electrons are just sort of swimming around that whole structure. They're not really bound in any one way. All right, so here, number one, in the solid state, metals conduct electric current uniformly in all directions. So this one is going to be true because, again, the structures are three-dimensional. The atoms are arranged into infinite arrays in 3 dimensions, cubes or hexagons being the unicell, but then those are going to be stacked in all directions. So the structures are three-dimensional, and the electrons are able to float throughout that whole three-dimensional structure. So the electric conductivity is uniform in all directions. Particularly true when it's a cubic unit cell, where, again, all the directions are the same. Okay, so that one's true. Here it says the bonding in most metallic solids is monodirectional. This is kind of the opposite of the above one. Now, it's talking about bonding here, but again, monodirectional means that the bonds would be in a single direction along the unicell, but again, in reality, it's three-dimensional again. So this one is false. Just like the conductivity is three-dimensional, the bonding is also three-dimensional. Or all directions, if you want to think about it that way. Okay, so that one's a false statement because the bonding in metallic solids, again, is all equal in all directions. There's not a single orientation to it. And then finally, 3, the electron C model, that's what we call metallic bonding, explains electrical conductivity of metals by assuming that the valence electrons move freely within the lattice. That's kind of a superposition of the last 2 points here. So this is also a true statement because, again, the electrons in metals are delocalized in all directions. They move freely within the lattice. And because they can move so freely, that allows them to conduct very easily through the solid. So the only false statement here, the incorrect statement, is going to be number 2. All right, so make sure you're familiar with the bonding, especially metallic bonding is what we talked about the most, but also band structures are kind of related to that, which we covered as well, so there could be final exam problems in that. All right, that takes me to the end of the very last homework review, so I hope you guys found these videos to be useful throughout the semester. Thank you for watching for those of you that did. If you have any additional questions about this material or anything else related to the final, please come find me in my office hours, which are posted on Blackboard, or you can send me an email and we can set up something individually. All right, thanks again for a great semester, and I wish you the best in your final exam.